Quantum chemistry, also known as molecular quantum mechanics, is a branch of physical chemistry focused on the application of quantum mechanics to chemical systems. This means we use the principles of quantum mechanics to understand and predict the behavior of molecules at the atomic level. In quantum chemistry, calculations play a crucial role. We use these calculations to determine electronic contributions to physical and chemical properties of molecules, materials, and even solutions. By doing so, we can predict structures, spectra, and thermodynamic properties, all of which are essential for advancing the field of chemistry. One of the key tools chemists rely on is spectroscopy. Spectroscopy allows us to gather information about the quantization of energy on a molecular scale. Common methods include infrared IR spectroscopy, nuclear magnetic resonance NMR spectroscopy, and scanning probe microscopy. Quantum chemistry helps in predicting and verifying the data obtained from these spectroscopic methods. Many studies in quantum chemistry focus on the electronic ground state and excited states of atoms and molecules. We also study reaction pathways and transition states during chemical reactions. A significant assumption made in these studies is the Born-Oppenheimer approximation, which assumes the electronic wave function is adiabatically parameterized by the nuclear positions. To achieve these predictions, a variety of approaches are used. These include semi-empirical methods, density functional theory, Hartree-Fock calculations, quantum Monte Carlo methods, and coupled cluster methods. Each method has its own strengths and is chosen based on the specific requirements of the study. At the core of quantum chemistry is the goal to understand electronic structure and molecular dynamics through computational solutions to the Schrödinger equation. This equation is fundamental in quantum mechanics, and solving it accurately for different molecules is essential for progress in the field. However, this is not without its challenges. Increasing the accuracy of results for small molecular systems and expanding the size of large molecules that can be realistically computed are ongoing challenges. The computation time increases significantly with the number of atoms, making it a complex task. But despite these challenges, the advancement in quantum chemistry is nothing short of magical. Chemical dynamics involves studying the motion of molecules, which can be understood by solving the Schrödinger equation with the total molecular Hamiltonian. This process is known as quantum dynamics. When we use the semi-classical approximation, it's referred to as semi-classical dynamics. Purely classical simulations of molecular motion fall under the realm of molecular dynamics, or MD for short. But the story doesn't end there. There's a hybrid approach known as mixed quantum classical dynamics, which combines elements of both quantum and classical mechanics. Another intriguing method is path integral molecular dynamics, which uses the Feynman path integral formulation to add quantum corrections to molecular dynamics. Statistical approaches, such as classical and quantum Monte Carlo methods, are also employed in chemical dynamics. These methods are particularly useful for describing equilibrium distributions of states, giving us a broader understanding of molecular behavior. One of the key concepts in chemical dynamics is the Born-Oppenheimer approximation. Introduced by Born and Oppenheimer in 1927, this approximation represents interatomic interactions with single scalar potentials called potential energy surfaces. Early applications of this concept were carried out by Rice and Ramsperger in 1927 and Kassel in 1928, leading to the development of the RRKM theory by Marcus in 1952. This theory allows for simple estimates of unimolecular reaction rates based on the characteristics of the potential surface. Non-adiabatic dynamics, on the other hand, considers the interaction between several coupled potential energy surfaces, corresponding to different electronic quantum states of the molecule. The coupling terms here are known as vibronic couplings. Pioneering work in this field was done by Stueckelberg, Landau, and Zehner in the 1930s, leading to the formulation of the Landau-Zehner transition, which calculates the transition probability between two adiabatic potential curves near an avoided crossing. Spin-forbidden reactions are another fascinating aspect of non-adiabatic dynamics. These reactions involve at least one change in spin state as the system progresses from reactants to products. Quantum chemistry A field brimming with both historical significance and modern-day marvels, unveils itself as a tapestry woven from numerous groundbreaking discoveries and theories. Some view the birth of quantum chemistry as starting with the discovery of the Schrödinger equation and its application to the hydrogen atom. However, a 1927 article by Walter Heitler and Fritz London is often recognized as the first milestone in the history of quantum chemistry. This was the first application of quantum mechanics to the diatomic hydrogen molecule, and thus to the phenomenon of the chemical bond. But before this pivotal moment, a critical conceptual framework was provided by Gilbert N. Lewis in his 1916 paper, The Atom and the Molecule, where he developed the first working model of valence electrons. Important contributions were also made by Yoshikatsu Sugiura and S.C. Wang. A series of articles by Linus Pauling, written throughout the 1930s, integrated the work of Heitler, London, Sugiura, Wang, Lewis and John C. Slater on the concept of valence and its quantum mechanical basis into a new theoretical framework. Many chemists were introduced to the field of quantum chemistry by Pauling's 1939 text, The Nature of the Chemical Bond and the Structure of Molecules and Crystals, an introduction to modern structural chemistry, wherein he summarized this work, referred to widely now as valence bond theory, and explained quantum mechanics in a way that could be followed by chemists. The text soon became a standard at many universities. In 1937, Hans Hellmann appears to have been the first to publish a book on quantum chemistry, in both Russian and German languages. In the years to follow, this theoretical basis slowly began to be applied to chemical structure, reactivity, and bonding. In addition to the investigators mentioned above, important progress and critical contributions were made in the early years of this field by Irving Langmuir, Robert S. Mulliken, Max Born, J. Robert Oppenheimer, Maria Goeppert-Meyer, Eric Huckel, Douglas Hartree, John Leonard Jones, and Vladimir Fock. As we stand on the shoulders of these giants, quantum chemistry continues to evolve, finding new applications in materials science, pharmacology, and nanotechnology.